National 5, we are back with a beautiful day in a tenement garden. Look at this, absolutely stunning. Now, Nova is going to want this ball, but I'm using this ball for an analogy to talk about three different energies. Ones that you already know from dynamics. That's kinetic energy, potential energy, and work done. Alright? So, Nova, sit. So first of all, we're going to do work done. Okay? EW equals FD. Now, work done is basically me lifting something up or pushing something with some sort of force over a distance. So if I was to show that here, it would be as if I'm bringing the ball down here and lifting it up and putting it on this wall. Okay? So that would be work done. Alright, Nova is going to want the ball. So this is work done. Now when I put the ball up to that wall there, then that becomes potential energy because AP equals mgh. Mass times the gravity of the Earth over some sort of height. Okay, so it's resting on this wall, so it's got like a height of 1.4 meters. Now, the conservation of energy states that energy cannot be created or destroyed, but only transferred. So I've transferred the work done now to potential energy. If I was to vanish this ball, that would then drop into kinetic energy with the energy it has from being at that height. Now, I'm now going to throw the ball. EK equals a half mv squared, so Nova's going to chase this. So EK equals a half mv squared is the kinetic energy of the ball. So it's a movement energy. Alright, so Nova's going to be bringing this ball back. She's getting a bit tired because I've done it quite a few times now. Let go. Let go. There you go, good girl. Whoa. So, that is kinetic energy. Now, all three are connected using the conservation of energy. You need to know what the conservation of energy is and how to identify that in a question. Sometimes it gives you height stuff that you then need to find out the kinetic energy with. So, all of that is something that you will do in your, first of all, in the past paper questions, and then second of all, in your Google form as practice for your prelim revision. Anyway, National 5, that's us done another episode of Mr. Bill's Physics. I'm going to keep chucking the ball out for Nova. It's a beautiful day, and I hope you have a good week. See you later. Alright, National 5, a bit of fun there outside in the beautiful day and in the tenement garden, but now we are moving on to prelim revision and talking about energy and not heat energy and nothing to do with heat, so all the other energy equations. So let's get going with this. So like, share and subscribe, guys. We're so close to the 300. Let's see if we can do it by Easter. Not going to go on about it. You know the drill. Let's do it. Now, energy revision. Plus also looking at power. I didn't talk about power in my video, but power is a very easy equation, so I'm just going to touch on it ever so slightly, so that means we've covered it. So we're going to do work done, gravitational potential energy, kinetic energy, power, and conservation of energy. I would say this stuff was fairly straightforward. Okay, this stuff should be getting marks in any exam, and I'm going to go through many examples today that will hopefully help you feel good about this part of the course. So let's look at work done. Work done is simply just, and again, sorry for the formatting issues, it's just a change in PowerPoint to Google Slides. Now, work is done when a force is applied to an object to move it at a distance. Work is done to measure the energy transferred. Now, obviously that's from when the ball was on the ground up to the wall in my video. Work done is in joules, force in newtons, and distance in meters, and it's EW equals FD. And a wee example, a boy finds he has to exert a force of 50 newtons to lift a box 2 meters onto a shelf. What is the work done? Well, we just do EW equals FD. Force times distance, which is 50 times 2, gives us 100 joules. Not very tricky, not very difficult. So, example 2, or number 2, sorry, gravitational potential energy. So remember when the ball was on the wall? We said it had some sort of potential energy, and is the energy gained when an object rises a certain height. So EP is the potential energy in joules, mass is m in kilograms, g is gravitational field strength in newtons per kilogram, and h is the vertical height in meters, not horizontal, vertical. So let's look at an example here where a woman lifts a 10 kilogram mass to a height of 2 meters. How much potential energy has the mass gained? Well, we know that it's just EP equals mgh, so 10 times 9.8, which is the gravitational field strength of Earth, times by 2 gives us 196 joules. I'm pretty sure you can trust my maths on this one. And how much work has she done? Well, by conservation of energy, we know that EP equals EW, therefore that means that EW is 196 joules. Okay, so we're going to talk about conservation of energy in just a second. I talked about it in the video, but it's the fact that energy is transferred and not created or destroyed. So, two easy ones. If you need to pause it and look at these examples, please do. I'm just going through this quite quickly because we have done all the stuff before. You guys know it. You guys can answer the questions, so it shouldn't need much description. Okay? So kinetic energy, number 3. Kinetic energy is the energy of an object when it's in motion. And again, there's a 2 there when it says EK equals a half mv squared. There's a 2 there by mistake, not showing up because of that yellow box. EK is the kinetic energy in joules, m is the mass in kilograms, and v is the speed in meters per second. So 2 examples. What is the kinetic energy of a 3 kilogram trolley moving at 0.8 meters per second? And the harder question that normally gets asked in these ones is a car of mass 1,200 kilograms has 614 kilojoules of kinetic energy. What is the speed? Okay, now if you're in my class, I give you an equation for the speed. It was just a rearranging. You can rearrange very easily if you're good at that, but if not, then it's just good to memorize the equation. Okay, so example 3, EK equals a half mv squared. It's just going to be a half of the mass, which is 3, times the speed, 0.8, and that 2 is meant to be a superscript 2. That's meant to be a squared, okay? So I do apologise. That 0.8 is meant to be squared, not just got 2 into it. So EK equals 0.96 joules, okay? So 0.96 joules for that. So example 4 then would say a car of mass 1,200 kilograms has 614 kilojoules, so we need to find the speed. This time I'm just going to put the numbers in for the EK equals a half mv squared. So remember that it's v squared. Again, that 0.8 is meant to be squared, not just 0.82. So it says 614,000 equals a half times 1,200 times v squared. So I half the 1,200 to get 600, and I rearrange it to get v squared equals 614,000 divided by 600, and that would give a speed of 32 meters per second. All right. So that there is kinetic energy. We're going to come on to conservation of energy, which is pretty much what most of the questions will be based on. So power. Again, we didn't talk about power in the video, in the beginning of the video, but it's just P equals E over T. We've done this equation lots and lots of times. Power is measured in watts. Sometimes, though, your questions get asked joules per second, and it kind of tries to confuse you. Joules per second is just a fancy way of saying power or watt. Okay? So power is defined as the amount of energy that is changed from one type to another in 1 second. Okay? So a good equation that always gets asked in conjunction with energy. Alright, so this is an example. A horse pulls a cart 20 metres with a force of 50 newtons. The journey takes 40 seconds. First of all, how much work is done, and then second of all, what power is generated. So again, first one's nice and easy. It's just EW equals FD because there's a force and there's a distance. So 50 times 20 is 1,000 joules. Okay, and then what power is generated? P equals E over T. 1,000 divided by 40. I'm just putting in the numbers. There's nothing tricky here. There's nothing trying to trip you up. And that would be 25 watts. Okay, you guys should be starting to get pretty good at your physics now. So I'm not spending too much time. You're starting to get to the peak of your physics knowledge. So last one is conservation of energy. Now this is important because these are the questions that are basically asked all the time in prelims and in exams. So basically what they do is they will ask you a question that will have information on it that doesn't match the actual question. So for example, you might be asked to find the kinetic energy or the speed of something, but you're only given things in the height. Okay, so therefore you need to find potential energy first and then do conservation of energy, saying that that's kinetic, and then you can then figure out the speed. So we're going to do an example, so don't worry too much, but here's a little slide for you. Okay, so in any transformation, the total amount of energy is conserved. Some may be changed into less usable forms. So if it is possible to calculate the total energy at one point, then the total energy is known at every other point. So for example, if you know the total energy at the top of a slope, then you will know that that is the same energy that will then be transferred to kinetic energy at the bottom of the slope. Okay? So another way of looking at it is that the work done in moving a trolley up the slope to the top will be the same as the actual potential energy at the top. Okay, and if I was to let that go and it was to come back and it would get down to the bottom, then it would actually be the same as the kinetic energy at the bottom of the slope. Okay, so conservation of energy is just the transfer of energy. Now, 2 things for these kind of questions. One is try the equation that seems to make sense. So for example, if it asks for kinetic energy, try that. Okay. And then if you don't have the required information, it must be an energy change. Okay, so remember the total energy is always conserved. So what we're saying, do what always makes sense first, and then if it doesn't work, you will have to use another energy equation because it will be looking for an energy change. So let's do an example. And there's plenty of examples in many past papers, but let's just do one here. Okay, so it says this: a 40 kilogram box is dropped from a height of 20 meters. So it says 1. What was the box's potential energy before the drop? What kinetic energy does it have when it strikes the ground? And what is the speed of the box when it strikes the ground? Okay, so lots of things there. So let's just look at the answers. What was the box's potential energy before the drop? Well, we just know that EP equals mgh. Let's just try it. We've got the mass, 40. We've got gravity, 9.8. And we've got the height, which is 20. So times all them together, you get 7,840 joules. Easy. Then it says, what is the kinetic energy does it have when it strikes the ground? Well, we know that this is an energy change because we know that it's going from some sort of height and it's been dropped now. So then, therefore, that's just a transfer of energy. So we know that by conservation of energy, EP equals EK, which therefore means EK equals 7,840 joules, the same as before. Why is that important? Because it's going to help us to answer 3. What is the speed of the box when it strikes the ground? EK equals a half mv squared. We just rearrange it again. 7840 equals a half of 40 times v squared. So half of 40 is 20, sorry. So then therefore 7840 divided by 20 gives us v squared. A square root of that answer would give us 20 meters per second. So again, easy way of doing it, step by step. Take a photo, stop it, pause it if you need to look at that again. But that is a classic conservation of energy question. Alright, so this is a sum up. These are the important equations that you need to know. EW equals FT, P equals E over T, EP equals mgh, EK equals a half mv squared. You will get lots of questions in both your multiple choice and in your written section on all of this stuff. So please take care, because these are fairly straightforward marks. Nash 5, another good one. We're on to the last one next week, which is heat, and then it'll be the Easter holidays. Very well done, and hope you have a good week with this work.